Hello everyone, this is my presentation for Lab 2, Lines of Charge. The purpose of this lab is to expand on the ideas of Lab 1 to get a clear understanding of how the electric force works in the real world. Instead of the naive approach used in Lab 1 of assuming that the charge of the tape was concentrated in the center of the tape, in this lab the tape will have its charge distributed across its whole length, which should be able to give us a more accurate calculation of the amount of charge needed to float one tape above the other. This new model found that the magnitude of the charge of the tape was about 1.1 times 10 negative 8th coulombs. Before we jump into what happened in Lab 1, Lab 2, we should go over a quick summary of Lab 1. And so first we created two tapes of the same charge, and we assumed that they have equal magnitude were created. And one tape was hovered above the other, meaning the electric force and gravitational force were equal and opposite forces. If that's a little confusing, we'll explain more about the physics principles used in both these labs in the next slide. And then by assuming all the force was concentrated in the center tape in Lab 1, is what we did, the charge of the tape was calculated to be about 3.9 times 10 to the negative 9th coulombs. So let's quickly go over what physics principles were involved. The most important one, which always seems to be the most important one, is Newton's second law, which is sometimes called the momentum principle. And this principle tells us if the momentum of a system is constant, then the net force of the system is zero, and of course the inverse is true if the momentum of a system is not constant, then the net force is not equal to zero. And then we have another form of physics principle is the electric field calculation, which allows us to find the electric force at a specific point when multiplied by the charge of that position using the equation here, and superposition, which is when you add up the electric field vectors at a specific point charge, you can find the net electric field at that point, which makes it easier to calculate the electric force in the manner described above. And the majority of this lab is focused on a new model of the electric force on the tape, where we model it by using a row of point charges of an arbitrary number, and chose 10 because it was a lot better than just having one point charge, but it also does not slow down the amount of time the calculations take. The net electric field and electric force were then found at each point and added together to give the electric force on the tape. With this, it was then possible to adjust the magnitude of the charge to find when the system was in equilibrium. Of course, there were a couple assumptions made, most notably that there was no air resistance on the force, and then of course, even though it's a less assumption than Lab 1, that the charge was evenly distributed, because there's probably points across the tape that have more charge than others. And then the most important part of the code, besides the electric field calculation, which has been detailed how that should be done before, is this nested loop, which calculates the electric field and the electric force at each point by summing up and then finding the total net force by summing up the total electric fields and then the total electric forces. And then using this electric force calculation, it is possible to adjust the magnitude of the charge of the tape until the magnitude of the electric force has the same magnitude as the gravitational force. And the most important part of this lab is comparing the results, where we can see that the charges found in the two labs are significantly different. This is basically due to our methodology of finding the charge, because Lab 2 assumes that the charge of the tape is evenly distributed across the tape as opposed to concentrated in the center. The charges not in the exact center of the tape do not have their electric force going in exclusively the positive y direction. So to have the force of the same magnitude as the gravitational force, or the force we found in Lab 1, the charge has to be greater, because some of that force, for lack of a better word, is lost because when you split the component in the x and y direction, the x directions, some of that force is in the x direction, which ends up being canceled out by an equal and opposite force from a different charge.